Ever tried learning to ride a bike by just watching videos? You might get the basics, balance, pedaling, steering, but when you actually get on the bike, you realize there's a whole lot of trial and error. That's the problem researchers are tackling with AI navigation models. Today, we're diving into a breakthrough study that's changing how robots learn to move through the real world. Here's the catch. Current AI models for robot navigation are trained on massive amounts of video data from the internet. They're great at spotting patterns, but they miss something critical: experience. Think of it like a chef who's memorized recipes, but has never cooked a meal. They know the ingredients, but when the stove's too hot or the pan's too small, they're stuck. In real-world environments, like busy city streets, robots need to react on the fly. They have to dodge trash cans, weave through crowds, and adapt to surprises. But models trained only on static videos can't feel the consequences of their actions. They're like passengers in a car, not the driver. That's where S2E comes in. Short for seeing to experiencing, this framework bridges the gap between watching and doing. It combines two powerful ideas: pre-training on vast video datasets and reinforcement learning, a method where AI learns by doing, getting feedback in real time. Think of it as teaching a robot to ride a bike by first showing them videos, the seeing part, and then letting them practice on a simulator, with gentle nudges when they wobble, the experiencing part. The magic of S2E lies in two key innovations. First, anchor-guided distribution matching. Imagine a robot learning to navigate by following anchors, like landmarks or goals in the environment. These anchors help the model generate diverse, realistic movement patterns, much like a hiker uses trail markers to explore different routes. This makes the model more reliable and adaptable. Then there's the Residual-Attention Module, which acts like a smart filter. After pre-training on videos, the model gets a chance to refine its skills in a simulated world. The module lets it learn new behaviors, like avoiding obstacles or predicting pedestrian movements, without forgetting what it already knows. It's like a musician practicing a new song while retaining their mastery of old ones. To test their ideas, the researchers created a cutting-edge benchmark called NavBench-GS. This tool uses photorealistic 3D simulations of real cities, complete with physics and interactive elements. It's like a virtual training ground where robots can practice navigating crowded streets or tricky intersections, without the risk of crashing. The results? S2E outperforms traditional methods by a significant margin. It solves a big problem. When you scale up AI models with just offline data, their performance often plateaus. But with S2E's mix of pre-training and reinforcement learning, the models keep improving. The study also shows that reinforcement learning beats simpler, fine-tuning approaches, proving that active learning is the key to real-world adaptability. Now, how did they make this possible? A key trick was using anchor points, intermediate goals that guide the robot toward its destination. Too few anchors and the robot gets lost. Too many. It overcomplicates things. The team found the sweet spot: 8 anchors. It's like giving a driver just enough traffic lights to stay on track without getting stuck in gridlock. But here's where it gets even cooler. The robot's eyes matter too. They tested different visual encoders, the part that processes camera input, and found that combining these with a technique called Gaussian mixture models, or GMMs, helped the robot make smarter choices. Think of it like a chef picking a recipe. The GMM has multiple styles, like different cuisines, and the robot selects one, then tweaks it. It's all about balancing precision and flexibility. The real magic happened in a virtual city called Urban Sim. Imagine a super realistic simulator where 256 robot clones practice at once. They tweaked everything: learning rates, training time, even the robot's confidence in its moves. The result? A navigation system that's both precise and adaptable, like a seasoned driver handling unexpected traffic. And the numbers? Wheeled and quadruped robots nailed over 90% of tasks in simulation. Even the complex humanoid, with its many joints, performed surprisingly well. Sure, it's not perfect, but that's the point. Real-world challenges are messy, and this model thrives in the chaos. So why does this matter? Because robots aren't one-size-fits-all. This research means we can train a single system to work across any robot, slashing development time and costs. No more starting from scratch for every new machine. It's like teaching a dog to fetch a ball, then letting it adapt to fetch a frisbee. The future of robotics isn't just about smarter machines. It's about systems that learn, evolve, and navigate the unpredictable world with confidence. Next time you see a robot navigating a crowded street, remember, it's not just following a script. It's learning, adapting, and mastering the art of real-world movement, one step at a time. Stay curious and keep exploring the cutting edge of AI.